These are your notes for section 6-9, and today we're going to talk about something called complex numbers. Okay, there's your journal choice. And here's what I got on complex numbers for you. When you have a real number and you add or subtract it to an imaginary number, that's called a complex number. They're complex because they have two parts. They have a real part and an imaginary part, so that makes them complex. Okay, it will look like this, a plus bi. We generally put the real part first and then the imaginary part second. Okay. If you do have the imaginary part first and then the real part, that is okay. So these two are equal, but most of the time I'd say people do write it like a plus bi. Okay. These are equal complex numbers because the real part is equal, 4 and 4. The imaginary part is equal, negative 7i, negative 7i. All properties of real numbers hold true. Everything that you expect to happen with these will happen. And there are applications in electricity. And I don't understand this at all. So if you want to ask Mr. Witt, he might know. I understand the math behind it, but I don't understand the electricity applications. So, I'm just going to be honest and throw that out there. Okay. It is commutative and associative. Multiplication, distribute. So you would still distribute it. 0 equals 0, I equals 0 plus 0i. This is what the additive identity would be. The multiplicative identity, if you multiply by 1, so if the real part is 1 and there's no imaginary part, it's still how you multiply. And every complex number a plus bi has an additive inverse. You could take the opposite of both parts. And the inverse of it, 1 over a plus bi. This should be one big long fraction bar. It's kind of hard to see. As long as it doesn't equal 0, is the multiplicative inverse. Okay, everything is what is the same as real numbers. These two numbers are called complex conjugates, and these are super important. You need to know this word, conjugate. That's going to show up a lot in your math career from here on out. The real part's the same, a and a. The imaginary parts are opposite. Okay, these are complex conjugates, and the reason is because if I was to multiply, FOIL, or double distribute those, the imaginary part goes away and you are left with just a real number. So here's the deal. It is not mathematically polite to have imaginary numbers in the denominator of a fraction. So like if I had 1 over 3 plus 2i, that's a no-no. So what we do is we multiply by that special variety of 1, which in this case would be 3 minus 2i, over 3 minus 2i. If you multiply by the conjugate, what happens is I can get rid of the imaginary number in the denominator. We double distribute. So 3 times 3 is 9. 3 times negative 2i is negative 6i. And do you see what happens here? 2i times 3, that's plus 6i. So those cancel out. Then I have 2i times negative 2i, that's negative 4i squared. And on the top, 1 times 3 minus 2i is just 3 minus 2i. Some of you right now are saying, you said you would get rid of the imaginary number, but there's an i down there. Well, there's an I squared, and I squared is the same as negative 1. So that becomes 9 plus 4, so now I have 3 minus 2i equals 9 plus 4 is 13. So 3 minus 2i over 13 is the exact same thing as 1 over 3 plus 2i. They look very different. You couldn't just come up with that by looking at it. But we multiply by that special variety of a 1, the conjugate 3 minus 2i over 3 minus 2i, because that equals 1, and it makes it look completely different, and it has a real number denominator, which is what we need in math. So let's simplify this one. 5 minus 2i, I don't know if you can read that very well, over 3 plus 4i. Again, you can't have an imaginary in the denominator. It's okay in the numerator, not okay in the downstairs, the denominator. So we need to figure out what can I multiply by that will get rid of that. And we're going to go with a complex conjugate, which will be 3 minus 4i. You have to do the same to top and bottom because we can't change this fraction. So we're just going to multiply that by 1. Okay, so I'm going to put parentheses around this because those are called the vinculum. They come with fractions. So let's double distribute. You want to do the bottom first to make sure we pick the right thing. 3 times 3 is 9. 3 minus 4i, that's negative 12i, plus 12i, so those cancel, just what I needed to happen, minus 16i squared. I'll move this out of my way. Here I get 15 minus 20i, negative 2i times 3 is negative 6i, plus 8i squared. Ugh, a little messy. It's okay though. I'm going to go down here now. So now I have 15 minus 26i plus 8i squared. Now remember, I squared is the same thing as negative 1, so that really is going to change that to a minus 8. 15 minus 8, this is going to be 7 minus 26i. Okay, on the downstairs, I'm going to get 9 minus 16i squared, which is 9 minus 16 times negative 1, which is 9 plus 16, which is 25. This is complete. I do want to mention, if all three of these numbers here had a common factor, you would have to simplify that. So just for future reference, if I had 2 plus 4i over 2, you do need to simplify, everybody. That would be 1 plus 2i. Okay, just keep that in mind. If all three parts have a common factor, you will have to simplify, divide out. Okay, this is fun. At least I'm having fun, so it doesn't really matter because I'm by myself right now. These are the types of numbers. We have so many types of numbers now. I feel like you're getting really smart. Complex numbers are at the top. Everything is a complex number. Okay? Because real numbers are complex because the imaginary part is just 0. And non-real numbers, obviously, those are your imaginaries. They could look like this, where it has a plus bi, where that's the complex that you're thinking of. Or they could be pure imaginary, where there's no real part. Okay, so there's no real part. Here, all those other numbers, rational numbers, those are 3 over 2 or 4, those things that you can make as a fraction. Irrational numbers, your square root of 2, square root of 3, and everybody's favorite friend, pi. Integers, negative 3, 7. Natural numbers are your counting numbers starting at 0. The whole numbers are missing here. Those are the ones that start with 0. These are numbers after 0. Whole numbers should be there too, probably. Okay? Lots of numbers. Numbers are our friends. They make us happy. Okay, pick and choose. I am going to go over all these. You can stop and fast forward the video as necessary. They want the real part and the imaginary part of each complex number. Real part is 6. The imaginary part is negative 8i, I think. Let me pause this for 1 second. Okay, I was wrong. I had to look that up. The imaginary part is just negative 8. This comes up every year. It's a plus bi. The I is telling you that it's imaginary, so the part they're curious about is the number value of the imaginary part. So they don't want the I, that's being a little bit redundant. They want the negative 8 only. Certain books do it different ways, and this textbook only wants that B number when they're asking for the imaginary part. Okay, this one says square root of 3 plus pi I. Real part, square root of 3. It doesn't matter if it's irrational, that's okay. And the imaginary part is pi in this case. They want the complex conjugate of 9 minus 24i. That's just to change the sign of the imaginary part, 9 plus 24i. It is not the opposite. A conjugate is not the opposite, so be careful with that. It's a special number that gets rid of the imaginary part. It's not the opposite. Okay, so this would be m plus ni. The complex conjugate is m minus ni. Okay, moving on. They want us to perform the indicated operations. I got 6 minus I and 5 plus 2i. We're going to do some double distributing here. 30 plus 12i minus 5i. So plus 12i minus 5i. Some of you do that in your head. Some of you like to write it down. And minus 2i squared. Clean it up here. 30 plus 7i. This is I squared. Minus 2i squared is the same thing as plus 2 because I squared is negative 1, so it changes that sign. Your final answer is going to be 32 plus 7i, and I should write that on line number 5, but I just ran out of space for work. I could throw out a box here on this next one. Okay, so let's look at 4 plus 3i squared. So I could do the shortcut that we talked about earlier this year. That's 16 plus 4 times 3i is 12i, double it, 24i, plus 9i squared. 16 plus 24i, this is the same thing as minus 9. It's going to be 7 plus 24i. Okay. This next one, I'm going to erase this too. Look at 7 here. It says 2 plus 6i times 2 minus 6i. Well, these are conjugates, so the imaginary parts should cancel out. 2 times 2 is 4. Minus 12i plus 12i. That's just what I needed to happen. Minus 36i squared is the same thing as plus 36. So 4 plus 36 is 40. And I'm left with a real number, which is just what I expected to happen. Okay, this guy. 1 plus I over 2 plus 6i. Nothing's really wrong with this except you can't have that imaginary down below. So I need to decide what can I multiply by that will get rid of that imaginary number in the denominator. It would be the conjugate 2 minus 6i on top and bottom. Lots of distributing to do here. So I get 2 minus 6i plus 2i, that's minus 4i, minus 6i squared, all over. 2 times 2 is 4. Minus 12i plus 12i, that cancels. Minus 36i squared. So this becomes plus 6 because of the 6i squared. So that's 8 minus 4i, all over 4 minus 36i squared. That becomes plus 36 because the I squared changes that sign. That's 40. This is what I was talking about. Good, I'm glad this came up. All three of these numbers have a 4 in common. If I take that out, I'm left 2 minus I over 10. Divide by 4, divide by 4, divide by 4. Okay? All right. Oh, didn't want that to happen. This is the electricity application I was telling you about. And like I said, I don't really understand the electricity application, but this is what it looks like mathematically. Basically, there's these Z things, and I don't know exactly what the Z things mean, but I do know they have imaginary complex numbers. They have imaginary parts and real parts. So here it says that Z1 equals 3 plus 5i, Z2 equals 2 plus I, and you do various things with these. So they want Z1 plus 3 Z2. This is just substitution, guys. 3 plus 5i plus 3 times 2 plus I. Do it just like if those were x's. So this is 6 plus 3i, 3 plus 5i plus 6 plus 3i. Combine like terms, 9 plus 8i. This is not hard. Just substitution. Okay? Z2 minus Z1. Again, substitution. 2 plus I minus parentheses. 3 plus 5i. Distribute that negative. 2 plus I minus 3 minus 5i. 2 minus 3 is negative 1. I minus 5i is negative 4i. We can multiply them, we can square them, we can divide them. I don't think you need me to do them all. I'll do one more. Let's do the division because I think that's the hardest math. I don't want to erase that. Z1 equals 3 plus 5i. Z2 equals 2 plus I. And we're going to do Z1 over Z2. 3 plus 5i over 2 plus I. Can't have that imaginary. We're going to clean that out by multiplying the top and bottom by the complex conjugate, 2 minus I. We're going to do some double distributing here. 6 minus 3i plus 10i minus 5i squared all over 4 plus 2i minus 2i, those cancel, minus I squared. I'm going to do some weird math and just write it on top here. This becomes plus 5 because negative 5i squared. So 6 plus 5, that's going to be 11 plus 7i I combine my like terms. It's going to be plus 1. 4 plus 1 is 5. So my answer is 11 plus 7i all over 5. Okay, so just lots of substitution on this page. And that's all I have for you today. All right, thanks.